We want to decompose this rational expression into partial fractions. To begin, you want to factor the denominator. This denominator has 4 terms, so we will factor by grouping. Grouping the first 2 terms together, we have a common factor of x squared. So factoring out an x squared will leave us with x squared times the quantity x plus 2. And grouping the last 2 terms together, we have a common factor of a negative 1, which will leave us with negative 1 times the quantity x plus 2. Now we have 2 terms, and they have in common an x plus 2. So continuing to factor, we'll factor out the x plus 2 and be left with x plus 2 times x squared minus 1. And then notice the second factor here is a difference of perfect squares, so we could factor him even more. And that will factor into x plus 1 times x minus 1. So the number of factors here tells us how many partial fractions we're going to have. So this is going to be a problem with 3 partial fractions. Our first denominator is x plus 2, our second denominator is x plus 1, and our final denominator is x minus 1. And we're looking to solve for the numerators. So my unknown is the numerator, which I'll just call capital A. So A will be divided by x plus 2. My second unknown is capital B, divided by x plus 1. And my third unknown is capital C, divided by x minus 1. So now we're going to proceed as if we're just adding the fractions on the right-hand side. And we know that to add fractions, we need a common denominator. And my common denominator will be found just by multiplying all of these denominators together. So we'll have a common denominator of x plus 2 times x plus 1 times x minus 1. So thinking back to your previous algebra class, when you're adding fractions, and looking at my first fraction, the denominator is x plus 2, so I need to multiply by x plus 1 times x minus 1. And what I multiply the denominator by, I also must multiply the numerator by. So I will also be multiplying the numerator by x plus 1 times x minus 1. So in other words, we end up with A times the quantity x plus 1 times x minus 1. And then we're going to do the same for B. We look at the denominator of B. B has an x plus 1, so it's missing, or it needs, an x plus 2 times x minus 1, so that it has the common denominator. And lastly, the last fraction, C, has an x minus 1, so it needs the x plus 2 times the x plus 1. And all of this is equal to 5x plus 7 divided by x cubed plus 2x squared minus x minus 2, which I'll go ahead and write in its factored form, since we already factored it. X plus 2 times x plus 1 times x minus 1. So now we have to do some algebra in this numerator, and we need to distribute. I'm going to opt to distribute the x plus 1 times x minus 1 first. So I'll have A times the quantity x squared minus 1. Same thing with the next term. I'm going to multiply x plus 2 times x minus 1 first. So that'll be x squared plus x minus 2. And the third term will multiply x plus 2 times x plus 1, which is x squared plus 3x plus 2. Now, at this point, notice that the fraction you have on the right and the fraction that you have on the left, they have the same denominator. So if the denominators are the same, then the numerators must be equal. Let me say that a different way. If you were to solve this equation, you would want to eliminate the division, so you could multiply both sides of this equation by that messy denominator. And that's going to allow you to eliminate the denominators. So we can eliminate the denominators and just focus on the numerators. So I'm going to go ahead and distribute on the right-hand side. So multiplying A times x squared, and then A times negative 1 when we distribute. Same thing, distribute in b. That gives bx squared plus bx minus 2b. And distribute in c. Cx squared plus 3cx plus 2c. Now we want to look at the left side and determine what will be equivalent on the left and on the right. So it's helpful to reorder the right-hand side. In other words, you'll notice that you have 3 terms that have an x squared. So let's go ahead and write those all together first. So we will have 5x plus 7 equals ax squared plus bx squared plus cx squared. Next, we'll write all of our terms that contain an x. So we have a bx and we have a 3cx. So plus bx plus 3cx. And finally, we'll write all of our terms that represent constants. Negative a minus 2b plus 2c. Now notice on the right side, the first 3 terms all contain a common factor of x squared. So now let's factor out an x squared, and we're left with x squared times a plus b plus c. The next 2 terms have a factor of x, so we'll factor out an x and be left with b plus 3c. And then the last 3 terms don't have a common factor, so we'll just list them. Negative a minus 2b plus 2c. So on the right-hand side we have an x squared term, but on the left-hand side we don't. So you can imagine it's as if we had an x squared term, but it was 0x squared plus 5x plus 7. And that may help you writing out the 0x squared so that you can see that 0 is the coefficient of x squared, and on the right-hand side the coefficient of x squared is a plus b plus c. So this gives us our first equation. A plus b plus c must equal 0. Moving on to the next term, my next term is 5x, so the coefficient of x is 5. On the right-hand side, the coefficient of x is b plus 3c. That gives us our second equation. B plus 3c equals 5. And then our last equation is found by equating the constants. So on the left side, my constant is 7, and on the right-hand side, the constants are negative a minus 2b plus 2c, and that will be equal then to 7. So now we have a system of equations. This is a system in 3 variables to solve. So we can solve this using elimination, or you could also solve it using an augmented matrix on your graphing calculator. Either method is fine. I'm going to go ahead and review the algebraic method of elimination here. So I like to label my equations as 1, 2, and 3 to stay organized. And you'll notice that your second equation, it only contains the variables b and c. So a has already been eliminated. Therefore, it would make sense to start with equations 1 and 3 and eliminate a. And you'll notice, if we do elimination and add equations 1 and 3 together right now, the a will be eliminated. So adding 1 and 3 together will give us the new equation, negative b plus 3c equals 7. Now we can put that together with my equation 2, which is b plus 3c equals 5, and do elimination again. And when we do elimination, the b's will be eliminated, leaving 6c equals 7 plus 5 is 12. So we can finish solving here, and we'll get that c is equal to 2. Then we can sub that back into any of our equations, but it would make sense to substitute it back into the second equation since it only contained 2 variables. So b plus 3c is equal to 5. But we just found that c was equal to 2, so we'll substitute in 2 for c. b plus 6 equals 5. So b is equal to negative 1. Then we take our c and our b value and take both of those and substitute them back into one of the originals, I'll go all the way back to equation 1. Equation 1 was a plus b plus c equals 0. So we have a minus 1 plus 2 equals 0. A plus 1 equals 0, so a is also equal to negative 1. So using elimination, we solved for a, b, and c. Finally, how do you write your final answer? Well, you go back to the original problem and you take a look at your original 3 partial fractions that you set up way back at the beginning. So our partial fractions were a over x plus 2 plus b over x plus 1 plus c over x minus 1, and we'll substitute the values that we just found for a, for b, and for c. So it was a divided by x plus 2, and we got that a was negative 1, so that's going to be negative 1 divided by x plus 2. Then our next fraction was b divided by x plus 1, and we got that b was negative 1 as well, so that would be negative 1 divided by x plus 1. And then our third fraction was c divided by x minus 1, and we got that c was equal to 2, so that would be plus 2 divided by x minus 1. These are our 3 partial fractions. Written another way, you could also write this as negative 1 divided by x plus 2 minus 1 divided by x plus 1 plus 2 divided by x minus 1. That would be acceptable as well.